What's up, guys? How you all doing? Hey, welcome to another video. Today we're going to be checking out a power monitoring system that you can build yourself using some ADCs, using some current clamps and things like that, and using our favorite Home Assistant added with ESPHome. If that sounds like something that'd be interesting to you, stay tuned because it's coming up right here, right now on MI Sperry. Okay, guys, so that's right. As the intro stated, we are going to be checking out how to build what you're seeing here. Now, this is my actual home one, so it's way more elaborate, so it's got a whole lot more stuff on it, but I'm going to show you simplistically with one sensor how to actually set all of this up. So let me get to our test bed and we will check out how to do this. Okay, so let's get into how it is put together here. So what we're going to do is we're going to take a peek at we're using a ESP32, so we're actually using the node 32, so that way it has a little bit more power to it. You actually get two I2C ports on this, so you can actually use two of the ADS 111.5, or what would it be? 1115, yeah. So you can use two of those if you want to, among other things, because it actually has two I2C controllers inside of it. So any case, you're going to just basically hook up the I2C data and clock. Pretty straightforward. You're going to hook up power and ground. Now, this is we're going to use the 3-volt side, and I'll tell you why we use the 3-volt side. You can use 5-volt. It's not going to make any difference. If you are wanting to do a custom application where you're going to be using this ADS 1115 chip all by itself, and you want to skip out on a couple of resistors here, the pull-ups for the I2C are internally pulled up on the ESP32. It actually does have internal pull-ups on it for that. So, however, they're only internally tied to 3.3 volts. So they are not tied to 5 volts. So if you use 5-volt VDD on this, or VCC, however you want to say it, but if you use 5 volts as your supply on the chip by itself, you will have to manually put external about 4.7K or maybe 10K pull-ups to 5 volts on your clock and data lines, because otherwise it won't work right. But if you use the 3-volt, then the ESP32 will use just its own internal. I think it uses, I can't remember if it's 10K or I think it's smaller. I think it's like 4.7K or something like that. It's what it uses as its internal pull-up. So you basically can skip out on two resistors, just FYI. Then next we will have our analog out and analog 1. What we're going to be doing is we're going to be using differential is what we're going to be doing. So basically a differential pair, because since this is an AC waveform from the current transformer, then we want our bidirectional signal so we can be a little bit more accurate. So, and that's what we're doing here with this 3.5 millimeter audio jack, is we are connecting up the sleeve and the tip of it. That's the two parts. If there's any ring terminals on it, and even on the CT itself, it'll have a ring, it'll have a tip, a ring, and a sleeve. The ring is not connected to anything. The CT is only connected from the tip to the sleeve. So that's what we're going to be doing here. We'll be connecting that to A0 and A1. And yes, you could put a secondary sensor on here and connect it to A2 and A3. And I'll show you later on in the code kind of how you can change that up and read two different sensors using one ADC card. So that's basically it for the hardware. Very simple hardware setup. Not too much stuff going on externally. So let's go ahead and get into the tough part, and that's going to be the coding. Okay, guys, so now for the fun part, and that's going to be coding this all up and setting it all up in Home Assistant. I finally got a VM set up so we can do all this Home Assistant stuff, and I don't have to worry about trying to blur out, my API codes or things like that. We've got a complete test environment set up, so we should be good. So, any case, what we're going to be looking at here, let me make sure my other environment is doing okay. I just want to make sure my Wi-Fi environment is working, because I've even got a test router set up, so that way you guys can see start to finish, won't have to blur anything, you can see exactly how it works. So we need to add the ESPHome device to this. Now, how to do that? It's pretty simple. We're going to go down here to supervisor, and it's just an add-on in the add-on store. So you're just going to search for ESPHome. Now I am using the Home Assistant IO version. You can download the add-on yourself and install it yourself if you're using, whether it's in a Docker container or you're using it installed on a Raspberry Pi, whatever. This is just a VM. I did the exact same thing on my Raspberry Pi that I am running my legit Home Assistant off of, my production Home Assistant, I guess you would say. I did this exact same method, and so I know it works with the Home Assistant IO version of the install for Home Assistant on a Raspberry Pi. So here we go. So we're going to go ahead and put in our name of our device. So I'm going to say power monitor, and yes, if you try to put spaces in it, it doesn't allow spaces. It will put hyphens automatically if you don't use spaces. So now we're going to put our SSID, and I need to pull that up because I just created it for my test network. So we're going to put in your network. So this would be like your home network or whatever network that you have your Home Assistant server attached to. This is the network that you need to be a part of. So for this one, we're just going to do my test, and that's our test network. I'm going to put our password in as testing. So put in your Wi-Fi password, put in your SSID, and hit next. Now it's going to ask you what type of device do you have. Now, if you do have a generic ESP32, like if you just ordered the ESP32 WROOM or room chip, and it's just the chip by itself, it's not a node MC or anything like that, you can choose that here by just saying ESP32 or just a generic 8266. Since we are using the node MCU 32S, we will go ahead and say pick specific board, and then from the menu we're going to choose node MCU 32S from the menu, so that way it knows which chip it's working on. So that way when you call out GPIO pins, it'll know what you're talking about. All right, so now that we've got it, it creates us a basically default node here. So what we're going to do is we're going to edit this node. So what it's going to do is it's going to bring in all of this information. And so what we're going to do is we're going to set down here below this captive portal. Now, you really don't need this, but if you ever wanted to, it goes ahead and builds like a hotspot active. And there's a way that if you lose connectivity to your device, let's say, you have to restore it or something like that, it'll actually broadcast its own Wi-Fi, and you can actually connect to it with your phone, and it has different menu options and things like that, which is actually kind of slick. That's kind of another video, but it does do that for you, which is kind of cool. So now we need to create some stuff. So we need to be able to build our I2C. We got to tell it that we're talking to a ADS 1115 sensor and all that stuff. So what we're going to do is we're going to start off by defining our I2C. So what I'm going to do, I think this is large enough for you guys. Yeah, I think it's large enough for you guys. Hold on, I got to like look between monitors here to see what you guys are seeing and then see what I'm seeing and make sure that it looks okay. Okay, so we're going to say I2C with a colon. Then I'm going to space in 2 spaces, give a dash and a space, and we're going to call out the ID of it, and I'm just going to name it bus A. Sure. Because like I said, you can have 2, so you can have like a bus A and a bus B, but it's whatever you want to call it. You call it main bus, backup bus, whatever you want to call it. Now I'm going to come under that ID, space in twice, and I'm going to define the data and clock pins. So our SDA pins, standard node MCU 32 is 21, and our SCL is 22. Okay, so that has that finished. So I'm going to drop down a couple lines, and now we're going to define our analog digital converter, ADS 1115, and then I'm going to indent a couple lines, give us a dash, an address. Now, you can have multiple addresses on this by playing with the resistors, but if you buy the ones from Adafruit or even the Jelly Bean ones that you can get off of AliExpress or wherever, or eBay or wherever you get them, generally they're always set up with address 48. So hex address OX 48. That's generally what they have them set up with, which that's taking the address pin that's on the ADC and taking that to ground through a 10K resistor is what it is. So that's generally what everybody does on those little breakout boards. So we'll add the address. I2C ID is next. We need to tell it which bus this one is connected to. So this is going to be our bus A, is where this is going to be connected, since that's the only one we have. But if you had 2 buses, you could connect the 2 different ones. So you could have the same address X48, if you had, let's say, another chip, and you could just connect it to bus B, and then define bus B up above, give it a new ID, like you would come up here and just give it another ID bus B, and then you just define SDA as whatever pin and SCL as whatever pin. So that's how you do that. And then we're going to call out what bus our ADC is belonging to. We also want to define our a quick ID to this one because we'll use this later. So I'm going to call it ADC0 is the ID of this one. And then we're going to turn continue. Hold on, I can't say it spelled at the same time. Continuous mode we're going to turn on, and that's for measurements. It will continually be pulling the ADC. You don't actually have to tell it down in further configurations like when to actually pull it or wait for something. It's just going to be always pulling the channels in the ADC constantly on the I2C side of things. And you want that because if you're doing measurements, you want things to be obviously as fast as possible. So it basically, an ADC will buffer up whatever it's doing, and you want to be updating that buffer all the time. So we'll turn continuous mode on. Now we're going to define our sensor. So this is going to be our integration sensor that will pick up in Home Assistant. So we're going to say sensor. So this is just like in your configuration.yaml file when you define sensors. It's literally the same type of setup. So we're going to call it a sensor. This is going to be a platform, if I can spell. This will be platform ADS1115. So, and then we're going to space in a couple spaces. Each time I indent, that's only 2 spaces. Okay, just FYI. So then we're going to give it the ID, ADS1115 ID. We're going to give it ADC0 because that's what we defined up above as our ADC. Then we're also going to give it the multiplexer command. Now, what this does is there's quite a few options for this. What it is it's asking us which pins are we actually going to be reading for this sensor. Is it going to be A0? Is it going to be A1? Is it going to be A2 or A3? You know, on the ADS or the ADC that we're using. So which pins, or is it going to be like we're saying the bidirectional versions of it? And for us, it's going to be the bidirectional versions, which is the ADC, or it's going to be in single quotes A0 underscore A1. And that means that we're going to be using the 2 pins A0 and A1 to measure the one sensor. So we're using that bidirectional ability that the ADS 1115 has available for us. So once we do, and so similarly, if you wanted to read the other one, you could create another sensor and just call it and call for A2 and A3 here. And that would get the other ones. Or if maybe you're just doing simple voltage measurements, you can just say A0 for one and then create a new sensor A1, create a new sensor A2, you know, and create basically 4 sensors out of it. Since we're using bidirectional because it's an AC waveform coming out of the CT, we're going to use 2. So now you got to specify the gain, which the gain is going to be determining what is the sensor range. Since we are using 20 amp to 1 volt CTs, meaning 20 amps is 1 volt and then everything, and then 0 amps is 0 volts. So we're scaling that 20 amps across a 1 volt region. So what we're going to be doing is we're going to be using a gain. Normally you would think a gain of 1.024, which would be like a volt and a little bit more, would be enough. But in experimenting and me playing around with it, really you want the 2.048 gain in there. And do those numbers make sense? 2048, 1024, right? It's all powers of 2. So that's it. And there's more. I'll leave links in the stuff below for the linking on where all the documentation is for all this down in the description. Gosh, I can't talk. All right, so now we're going to tell it how often to update this. So update interval is going to be 2 seconds is what we're going to do. So every 2 seconds, it's going to basically get us a new number. So it's going to check every 2 seconds. All right, now that we've done that, we're going to give it a name. So that way when it appears in our integrations as sensors, it'll have an actual name. So we're going to give it a name. We'll just call this one channel 1 raw. And this will be the raw measurement. This will be the raw voltage coming out. Once it has read the voltage, ADC'd it, and then applied the gain back to it, because what the gain also does is it basically calculates how many volts per count it's going to be, because it's going, you know, this is an ADC, right? It's going to ADC and give us, you know, probably 1024 or something like that. Well, what is 1024 in voltages? And that's what the gain helps us do. The gain is showing us, it gives it the right multiplier, so that way when it converts it back to actual voltage, you get the correct value. So this is going to be the raw voltage representation. It won't be the current representation, the voltage representation, okay? So channel 1 raw. Then what we're going to do is we're going to go down into here and define our accuracy. And so what that's going to be is our accuracy decimals. I'm going to give it 3 decimals, so it'll be like 0.000 after the end of it, just so you know, you never know. We're being down in the millivolt region anyway, so 3 decimals is plenty accurate for what I'm going to go with. And then we want to give it an ID, because we will reference that later, because I got another sensor that I want to build along with this. So that's it for our first sensor. So that's going to be our raw sensor. Now, the raw sensor bounces around a bunch because of, you know, noise and other things, and it can wiggle woggle around and do different things. And I also noticed that they have a really good platform that's in here. So I'm going to create a new one called CT Clamp. Now this is supposed to convert your voltage numbers into current numbers. The problem with it is it always assumes that it's a 1-to-1 basis. So 1 volt means 1 amp is what it's thinking. So we have to do some manipulation with that to multiply it up to 20 amps per 1 volt. Not 1 volt is 1 amp. Okay. So we'll do that later in Home Assistant. For right now, we're just going to do it here. You could do it here. I just noticed that when you get a whole bunch of sensors, like I wanted to do 32 sensors, if you're doing the math on all 32 of those sensors, it actually ends up choking the processor on the ESP32, and it literally can't process it. You'll get boot loops. So there's the thing. If you start getting boot loops, troubleshooting tip, reduce your code size, reduce how many sensors you have, and see if it doesn't fix it, and reduce the complexity of your sensors, and that may do it. So basically, if you can do things in Home Assistant math-wise and not have to do it in the firmware here, it actually helps out your processing on your ESP32 device, and it won't go into boot loops and kernel panics and things like that, because that happened to me. All right, so we're going to go into this, and this one's really simple. We're just going to call it sensor. We're going to call what sensor are we using to calculate this with. We're going to call our Chan 1, which is our channel 1 sensor. So that way it knows which one we're going to be, you know, calculating the current off of. And then we're also going to give it a name. We're going to call it channel 1, let's see, current. Sure. And then we're also going to say update interval, and we'll give it 3 seconds. So that way we give a second of kind of like steady state before we calculate this one. So that way the other one is updating every 2 seconds, and then we're just basically at 1 second later, we're grabbing it for the CT clamp, basically sensor calculation. So that is going to be pretty much it. And then you check for any errors. Usually it will show you, like right now I've got one. It says while phrase and blocks connector address 48. So it doesn't like my address 48. Oh, I see why. I didn't indent my stuff. This all has to go under the address 48. There we go. So I'm sure that'll be happy now. Yep. And how I noticed that was up there and I didn't see it was because your install will be grayed out. Like, I don't know if you saw that. Like, I don't know if I probably typed something that's not right or that's indented wrong. Yeah, see it go to grayed out, so you can't install. That's how you know that you probably got some sort of error in your code here. So there we go. So now let's go ahead and save it. So now we'll go ahead and program our device. So what I've done is I have plugged in, it's actually behind me sitting on a bench. I've got it all wired up. I have it USB plugged in to the VM technically, but you have to have it plugged in to the device initially. Okay, you can update the code and things over the air, but to initially get it on there, there are ways, and I'll show you when we hit, in fact, let's just do it. If we hit install, it has plugged into this computer, which means the computer that I'm using to work on this, which may not be the actual server. I haven't really gotten this to work. If anybody has, let us know in the comments, but I haven't really gotten that to work. The main one that I've got, you've got a manual download, which if you have just a flasher, basically, if you have whatever it is. I think Arduino, if you have the Arduino IDE or something like that, you can just install it. You know, it'll just puke it out as firmware and you can just install it. Or if you have it plugged into the USB port on the server, so like I would plug mine into my Raspberry Pi that's in the back, you know, and do it this way. If you have it plugged into the server, then you can say plug into computer running ESPHome, and it'll basically find it. So there it is. So there's the USB, the UART bridge controller, and you just click it, and then it should compile and install it. Now it may take a little bit because it's going to compile through all the different libraries that are available. And there may be some errors here and there. When you watch the errors, you just watch and make sure that you don't have any weirdness. So I'm probably going to speed up the camera because I don't want to stop it because it goes straight into logging what happens. So I may speed up this process, but I won't stop the camera. Okay, we're getting close to being finished here. So it looks like it's finishing. So now it should boot. And it will look for, yeah, it looks for your wireless. Looks like it got connected up. And now it is reading voltages. So I'm gonna back up in this log here and show you what it's seeing. So finished successfully. Then it gives you the compile date, whatever. Then it comes down and activates the Wi-Fi. First, it scans for Wi-Fi. So there's like some different Wi-Fi stuff that's near me. And then it finds my test. That's the one that I coded it for. So it finds that one and then gets the IP address and everything. This is kind of nice. The signal strength, I like this because on some of the ones I have scattered way out there, sometimes they have trouble connecting, and I can play around with antennas or play around with position, and I can tell whether I'm getting more dBs or less dBs. You know, I'm getting more signal strength or I'm getting less signal strength. So if where I'm putting it is worse or better. So I kind of like that. I kind of like that feature that it gives you the signal strength right off the bat. And then it comes down through here and begins, let's see, setting up the sensors. Here we go. So debug, setting up ADS. So basically if it can't reach the ADS, if you've got the pins wrong, maybe clock and data reverse or something, it'll tell you right here that it can't find the sensor or something like that. It'll tell you what's going on. But there's pretty much everything. It's showing me setting up everything, or showing it setting up everything I wanted. And then now it's off and running, and if I scroll to the bottom, it just every 2 seconds it's gonna update the voltage value, and then every 3 seconds it's gonna update the amperage value. Okay. So there we go. So now this is working. This should end up going online. It could be the way that my my VM's set up. It may not show that. Let me get off of it and come back. Will it show it? It's not going to show it. The way normally it'll say online, it's just with the VMs, you have to do all this natting and port forwarding and all this crazy stuff. And so I don't get the status here, but I assure you it is working and it is delivering information.